In general, there are 4 common methods for humidity calibration, and they are a simple comparison, divided flow chamber, saturated salts, and the 2-pressure system. Simple comparison is just that. One device is placed next to another. And again, it's important to remember that it's the surrounding environment that is the reference. Temperature gradients are typically a big problem, and simply being present in those conditions will change the humidity and can cause additional errors. Typically, this is just a sanity check for a device operating. I would be reluctant to call it a true calibration. Another common method used for calibration of humidity is a divided flow chamber or generator. We can see in the diagram we have 2 air streams. One is dry air, the other is wet air, and both of these air streams are controlled with valves, and the resulting air streams go into a chamber. And it's in that chamber that the device being calibrated is placed. The humidity inside the chamber is measured through the hygrometer, and this hygrometer goes to a controller which turns on and off the control valves. So for example, if we're trying to maintain 50% RH, and we'll say it's dry outside, we'll have to add more wet air in order to maintain that 50%. So the hygrometer will monitor that humidity is dropping. The controller will turn on the wet air stream a bit more in the valve, and wetter air will go into the chamber, and that will bring the humidity up. Now, the problem is that the temperature of the 2 air streams is typically different. And it's not hard to imagine very dry air may have different temperature than very wet air. And the result is that we will not have good temperature nor good humidity uniformity when the 2 mix. So this can be a problem when we're trying to get good uniformity within the chamber. Chambers can also be affected by the external temperature fluctuations typically present when the HVAC kicks into either cool or heat. Another method that is occasionally used for humidity calibration is saturated salts. Now we can see in this diagram we have saturated salt slurry. Now this is a particular chemical salt that's mixed with water to the point where the water will not accept any more salt. It's saturated, in other words. That's contained within a sealed container, and the devices being calibrated are isolated here from a protective screen. Now the RH value in this chamber is a function of the physical properties of a particular salt. In this table we can see some common salts that are used for humidity generation. Here, lithium chloride, approximately 11%, potassium carbonate, and even sodium chloride are commonly used. Now, I've shown here the humidity generated as a function of temperature. And, you know, that looks pretty good. And one might conclude that saturated salts are not temperature sensitive. But these temperature coefficients can be very misleading, because these numbers assume that the system is in thermal equilibrium. And going back to that diagram, we can see that the saturated salt slurry, it's not hard to imagine that it has a very different thermal mass from the air above it. And if there's any small changes in the ambient temperature, the temperature of that salt slurry will be very slow to change compared to the air. The system will not be in thermal equilibrium, and the humidity fluctuations can be very extreme, many percent of RH from even a small temperature change. So saturated salts can provide a reference value, but it's very important to ensure that the system is very thermally insulated or isolated to ensure that it stays in thermal equilibrium. Also, these salt solutions can degrade over time, and it's also very important that the saturated salt solution not come in contact with the measuring device or its probe. It can cause contamination and change the humidity that the sensor sees, or it can even cause corrosion of the instrument. Another humidity calibration method is the tube pressure system. Now, this is considered a primary standard. Now, in this case, we can see an airstream that goes through a saturator, which brings the airstream to nearly 100% relative humidity. This airstream then goes to an expansion valve and then to the chamber where we will put the device being calibrated. The saturated air is produced at a known temperature and at a pressure that can be controlled. Now, if we were to take this saturated airstream and have it at, we'll say, 2 atmospheres, it's at 100% RH and at 2 atmospheres. We then bring it through this expansion valve into the calibration chamber, which is at room pressure, which is 1 atmosphere. We've taken the 2 atmosphere 100% airstream, brought it to a 1 atmosphere airstream. And what's happened is that the humidity at 1 atmosphere, or room pressure, is now 50% of that 100%. So by controlling the pressure of the airstream, we can control the relative humidity. And as we see here in the diagram, the relative humidity is equal to the pressure of the chamber divided by the pressure of the saturator. This allows us to generate relative humidity by simply measuring pressure and temperature. Both of these parameters can be measured and controlled with high accuracy, and that allows a humidity value to be generated very accurately without having to directly measure the relative humidity. And that's why this is a primary standard for generating humidity. Now, within a chamber, dew point, which is a representation of the amount of water vapor, that's quite constant within a chamber. That does not fluctuate with temperature like relative humidity does. Now, in this diagram, we're showing the device under calibration, the DUC. This is the device that we're trying to calibrate. We're also measuring the dew point within the chamber, in this case using a chilled mirror hygrometer. And we're utilizing an accurate temperature thermometer that's closely located to the device being calibrated. The dew point is constant throughout the chamber, and by knowing the temperature right at the device being calibrated, we can calculate the exact relative humidity right at the point of the device that is being calibrated. We can then use this as the reference value for the humidity calibration, and this can result in very accurate relative humidity calibrations. A growing number of industries require the use of accredited cal labs. The accrediting body audits each link in the traceability chain. They also assure that accurate statements of uncertainty are being presented, and they assure the use of proper calibration procedures and equipment. It's worth noting that the FDA themselves have become accredited in their own cal labs. So in conclusion, relative humidity is an important parameter because it can affect many materials and processes, and it often needs to be measured and monitored. There are many possible sources of error in relative humidity measurement. By being aware of these error sources, hopefully you can quantify them, and if not eliminate them, at least reduce them. I've personally been involved with humidity measurement and monitoring for over 15 years, and I have made every one of the mistakes and errors that we covered in the presentation today. In fact, those were the basis for this presentation, some of the hard-learned lessons that I've lived through. Hopefully you can learn from my mistakes, and I hope that you don't have to repeat them. Thank you very much for taking the time to watch and listen, and I hope it was of value to you. Thanks again. I'm Kevin Bull from Veritech, a Vaisala company.